Hi everyone, so we'll continue where we left off last time. So we'll solve question 5. So we know by what I did earlier that if A divides B, then the absolute value of A is less than the absolute value of B. And moreover, if B divides A, we have that the absolute value of B is less than or equal than the absolute value of A. So therefore, the absolute value of A is equal to the absolute value of B. So then that means that A is equal to the absolute value of B, or negative A is equal to the absolute value of B. So it follows that A is plus or minus the absolute value of B. So then we have that this tells us that unwrangling the absolute value of B as a definition, we have that A is equal to plus or minus B. Okay, so let's go on to question 11. If n is an element of the integers, what are the possible values of A being the GCD of n and n plus 2, and B the GCD between n and n plus 6. So let D is n, the GCD between n and n plus 2, and then D divides n plus 2 minus n, which is 2. So it can be all the possible divisors of 2, which is 2 and 1. So D is equal to 1 or 2. Because we know that D has to divide n and has to divide n plus 2. So in particular, it has to divide their subtraction. And so then D has to be part of the factors of 2. So the possibilities are 1 and 2. And similarly, B is D is equal to n and n plus 6. And then we have that D has to divide n plus 6 minus n, which is 6. So then it has to be one of the divisors of 6, which is 1, 2, 3, and 6. So D can be any of that options. And those are the only conditions that we have on or 6. Those are the only conditions we have on D. So let's look at question 13 next. Suppose that A, B, Q, and R are integers such that A is equal to BQ plus R. Prove each of the following statement. Prove each of the following statements. Every common divisor of C of A and B is also a common divisor of B and R. So let's prove it part by part. So if C is a common divisor of A and B, then we can write R. So if C is a common divisor of A and B, then we can write R as A minus BQ. And because C is a common divisor of A and B, so that means we can write C as C times K. That gives you A as C reaches A through an integer, and same thing with B. So we can factor a C, and we have that R is also a common divisor of C. All right. So let's continue. Every common divisor of B and R is also a common divisor of A and B. So what this gives you is the following. if you have A is BQ plus R, then if you have a common divisor, C prime of B and R, then you can express A as a multiple of C prime as well. So if C prime is a common divisor of B and R, then A is equal to C prime times K prime times Q, and C prime times U prime reaches R. So then if we factor in a C prime, we get C prime multiplied by K prime plus times Q plus U prime. So that means that C prime divides A and it divides B. Divides B. All right, so then we can reach the following conclusion, that the GCD of A and B is BR. So if D is the GCD between A and B, so in particular, D is a common divisor of A and B. So in particular, by what we've proven earlier, that for part A, we can see that D divides B and R. So in particular, it must be less than the GCD of B and R. So let's do that. So by part A, any common divisor of A and B is a common divisor of B and R. So we have that D divides A and B. So by part A, we have that D divides R as well. So D divides B and R. So because D prime is the greatest common divisor of B and R, so in particular, D. So in particular, we must have that D is less than D prime. And analogously, we have by part B, D prime is a common divisor of B and R. So D prime divides A as well as divides B. So therefore, since D prime is a common divisor of A and B, it must be less than the greatest common divisor of A and B. So D prime is less than the greatest. So we get the equality. So D is equal to D prime. All right, I'll end the video here. Thank you.